Hi, Emma. Really glad you could come.
Hi, Professor. Nice to see you.
Nice to see you. Let's start in on this cardinal stuff. All right. How many pieces of fruit, how many apples do you have in your bowl?
Uh, three?
Yep, exactly three. How'd you get it?
I counted.
What do you mean you counted?
Well, okay. One, two, three. Is something wrong here?
No. That's perfect. But like, why didn't you get five? Like, here we go. One, two, three, four, five. There are five apples in the bowl.
Well, because you counted some pieces more than once, and you're not supposed to do that.
Okay, I get that, but how come you didn't get two? One, two.
Well, again, you messed up. You didn't count one of them.
Hey, Emma, I'm the prof.
Well, yeah, you didn't count everything like you were supposed to, unless I'm the one that's missing something.
No, you are right, Emma. You're exactly right. But when you're counting, there's actually a lot going on upstairs. Let me share this page. So in your head, when you are counting, there is a collection of fixed sets that you've already dealt with by experience. And when you're counting, like you did with your finger, you begin with one and you match that with one apple, and with the number two, and you match that with a second, and the number three, and it matches that with a third apple. And then you're all done with the apples. And the number at the end of your list, in this case, the number three, is how many apples you say are in that bowl. This is the counting process. It involves a fixed set that's already in your head, plus this idea of matching. And matching functions are one-to-one, meaning you can't count something twice, and they're onto, meaning you have to match everything. So a lot's really going on when you're doing counting.
Okay, so sort of like I have a database in my head with sets and counting numbers on it.
Wow, that's exactly right. And so in what we had before,
Yeah, that didn't look much like me.
well, it wasn't supposed to actually look like you, Emma. I'm sorry about that. Um, but it is sort of elementary. And in fact, this idea of counting gets ingrained so early on that it seems more like common sense, but it's really a little bit more than common sense. But I apologize for your hairstyle. So let me show you how this matching goes. And I'm going to give you a couple of extra numbers that perhaps you haven't had before. So on the left are the numbers that signify number of elements. These are called cardinals. The number 0 is a cardinal number, meaning the set has nothing in it. The cardinal number 1 means a set has one thing in it. And the target sets that are official in mathematics are there in the right. The empty set is the official target set for 0. And the set that contains the empty set has one thing in it. And that is the official target set for the cardinal number 1. And so it goes. So the cardinal number 2, the official set is the set that contains the empty set and the set containing the empty set. And you might work out the next couple. But the two I wanted to show you are at the bottom. The first set is a set of all natural numbers. It's an infinite set, and its cardinal number is Aleph 0. Aleph is the first letter of the Hebrew alphabet, and it represents the first infinite cardinal number. And the second one is a German fractor C. C stands for continuum. And the continuum, or another name for the interval 0, 1, is called the continuum. And it has the cardinal number C. So these are actually numbers just like 1, 2, 3, and 0, and so on.
So these are infinite numbers?
Yeah, exactly. These are infinite numbers. So they have the two symbols, Aleph naught and C.
Interesting. Are there other infinite numbers?
You bet there are. In fact, there are infinitely many infinite numbers, and they're all lined up. So given any two, one's bigger than the next. And one interesting thing is there are actually more than infinitely many infinite numbers. Maybe that's for another day, though.
Okay, so I think we proved that the German fractor C is not the same as Aleph naught in 344, or maybe ERA.
Yeah, usually that's part of the course, and the fact that those are not the same number. There are different ways to say that, but if you haven't seen it, let me know and we'll go through the proof. The proof uses the famous Cantor diagonal process, which is one of the famous proof techniques that should be in your toolbox. One last thing, though, is that nobody knows if C is equal to Aleph 1. That is, if the second infinite cardinal, and there is a second infinite cardinal, if the second infinite cardinal is C. And this is called the continuum problem.
Fascinating.
Yeah, that won't be part of our, we won't have to solve that this spring, but it is interesting.
Very interesting.
Well, thanks a lot for coming, Emma. I really appreciate it.
Yeah, thank you. This was very interesting. I learned a lot.
Great, me too.